Welcome all of you. In the last class, I just started giving basic introduction to NMR spectroscopy. I introduced some terms of spin physics like spin angular momentum, spin quantum number, magnetic moment, magnetic quantum number, gamma, and different nuclei, how we can find out the spin of the nuclei by using some empirical rule, and what is the difference between two nuclei if they have the same spin quantum number I and same magnetic quantum number m. And I showed the gammas are different because masses are different, and I said the nuclei with different gamma can be individually studied. So with that, I also wanted to tell, I also calculated magnitude of the angular momentum also, and we said the spin angular momentum is quantized along z axis, and using that we found out what is the theta, the angle at which these mi equal to plus half and minus half are oriented with respect to the magnetic field. Today let us start discussion about Zeeman interaction. So Zeeman interaction, one of the important requirement for NMR is the interaction of the magnetic moment mu with the static magnetic field B naught. So this is very important thing. Okay. Nuclear spin quantum number I must be non-zero. Remember, this must be non-zero to detect NMR. As I told you in the previous class, when I equal to 0, mu is 0. When mu is 0, there is no question of interaction of the magnetic moment with the external static magnetic field. So NMR cannot be observed. So the nuclear spin quantum number I must be non-zero to see NMR. So this formula we already worked out. I showed you mu is equal to gamma into h cross into root of I into I plus 1. Of course, mu is also a vector. In principle, we can put an arrow about it at the top of it. Now let us see how the mu interacts with the magnetic field V naught. Nuclear spins, you take nuclear spins, put it in an external magnetic field, static field, huge, whose strength is very large. I call that magnetic field B naught. Then what is going to happen? Some nuclear spins align in the direction of the field, some align in the direction opposite to that of the magnetic field. There are two possible orientations we can think of. Because I am dealing with spin half nuclei, remember, unless otherwise I mention, most of the time I will be dealing with spin half nuclei. And when the two orientations are there, two possible orientations of the nuclear spins in the magnetic field, their energies of interactions are also different. The energy of interaction of the spins in this direction and the energy of the spins in the direction opposite to the magnetic field, these two are different. Okay. So when the two energies are different, what is going to happen is, once you put it in a magnetic field, they get separated out like this. This is called removal of degeneracy. The degeneracy is going to be removed, and this is called Zeeman effect. This interaction of the magnetic moment with the external magnetic field is called Zeeman interaction. Okay. Now for spin half nuclei, the interaction energy is given by E equal to minus mu into B naught. Both are vectors. It is a dot product. And there is a negative sign for that. We will come to that later. Now we can see for spin half nuclei, in the absence of the magnetic field, all the spins are randomly oriented. There is no preferred alignment. You can see spins aligned both in the directional field, in the direction opposite to the field, etc. There is no separation of the energy levels. Moment you put it in a strong, these are called degenerate states. Moment you put it in a magnetic field, static magnetic field, which is non-zero. As I told you, there is a separation of energy levels because the spins orienting along the direction of the magnetic field and opposite to the direction of the magnetic field, they get separated out. The energy levels get separated out. This is called removal of degeneracy, and the energy states is one corresponding to anti-parallel orientation of the spins with respect to magnetic field, other is parallel orientation, and this separation between these two energies is called delta E energies. And you can see some spins which are oriented opposite to the direction of the magnetic field which I have written in the here, you can see they are all inverted. They are in the opposite direction, opposite the magnetic field, and these are all in the direction of the magnetic field. And now what we did by putting the sample in a magnetic field, we removed the degeneracy. That is what is important concept. This is because the nuclear magnetic moments interact with the external magnetic field. The energy of interaction of the magnetic moment with the magnetic field we will calculate now. As I said, E equal to minus mu into B naught. You may ask me a question, what is negative sign? What is the meaning of telling energy being negative? It is to ensure that spins orient in the direction of the magnetic field. The spins oriented in the direction of the magnetic field has lower energy compared to the one which oriented in the direction opposite to the magnetic field. This is a convention. To bring in this concept, negative sign is put. So, we continue further. Both are vectors. Mu is a vector, B naught is a vector, and we can resolve them into three components, x, y and z directions. So, it can be written as E equal to minus of mu x bx, mu y by plus mu z bz. And we always assume magnetic field to be aligned in the direction of the applied in the direction of the magnetic field, z axis. Z direction is the direction in which we apply the magnetic field. So, as a consequence, we can remove x component, y component, it will go to 0, and we are left with only E equal to minus mu z into bz. This is the energy of interaction of the magnetic moment with the magnetic field B naught. Now, substitute for mu z. We already worked out what is mu z. Mu z equal to m into h cross into gamma. That is what we worked out already. Substitute that, and this can be equated to m into h cross into omega naught. What I did, gamma into bz, I equated it, I replaced by a term called omega naught, is an angular frequency, where minus n is also included. Omega naught is equal to minus into gamma bz is the term. So, I replace omega naught and by minus gamma into bz, and this is the energy of interaction. Now, energy for two spin states alpha and beta, I can resolve them. I can find out E alpha, energy for the alpha state. We can write it as m is equal to half. Go back in the previous equation, see m is equal to half there. So, m equal to half and minus half, you put it, minus half into gamma h cross into bz over 2 pi. Instead of h cross, I have written h over 2 pi. E beta, same, half into h into bz over 2 pi. Please remember the change here. Alpha is plus half state. Because energy is minus, it is minus, and beta is minus half state. Because it is minus into minus mu to beta mu dot b naught, it becomes positive. So, EB is positive, E alpha is negative. Okay. So, notice because of that, energy state of beta is more than that of the alpha state, and in the absence of the magnetic field, if I write this as the alpha state and this as the beta state, as soon as I put in the magnetic field, this is the energy state. Beta is higher energy than that of the alpha state. Okay. So, remember this is up and this is down, and before the magnetic field, this is alpha and this is beta. Okay. Now, find out the difference in the energy between alpha and beta spin state. Delta E is equal to gamma into h into B naught over 2 pi. Now, you all know in atomic physics you would have studied energy is related to frequency. Delta E equal to h into nu. Now, equate these two, then it will become, and do some mathematical rearrangement, then you can find out and show that nu is equal to gamma into B naught over 2 pi. It is the famous equation NMR. Please remember, this is called a resonance condition. This is a beautiful equation which is responsible for giving several Nobel Prizes in NMR. So, this is a resonating condition. Nu is equal to gamma into B naught over 2 pi. This must be in your fingertips all the time. Okay. So, what is that you are going to observe here? If I take this resonating condition, nu is the frequency, gamma is a gyromagnetic ratio for a given nucleus, B naught is the magnetic field, 2 is constant, pi is constant. We know the value of pi. Everything is constant, gamma is constant, 2 is constant, pi is constant. If I keep the magnetic field B naught constant, that means for a particular value of B naught, frequency is constant. It means if I double the magnetic field, frequency gets doubled. It shows the resonance frequency vary linearly with the magnetic field. That is the important condition. So, nu varies linearly with the magnetic field B naught. So, this can be seen like this. How does it affect the energy states, difference in energy? For example, for a given magnetic field B naught, let us say at 200 megahertz correspond to 4.7 Tesla the magnetic field, and alpha beta are separated like this, and I can calculate the energy. This turns out to be 200 megahertz. Now, I will double the magnetic field, go to 9.4 Tesla. What is going to happen is, you can see that energy separation gets doubled, and if you calculate the difference in the energy, it turns out to be delta is equal to 400 megahertz. So, double the magnetic field, resonating frequency get doubled. Most important concept here you should remember, higher the magnetic field, higher the sensitivity and higher the resolution. That is why we always want to go to higher and higher magnetic field, so that we get better resolution and better sensitivity in NMR. The resonating frequencies at different magnetic field strength can be given like this. For different magnetic field strength, you can see, for example, 200 and 400 is exactly doubled, 200 and 800 you can see exactly 4 times. You can find out. So, this is varying linearly. Now, the question is, where does NMR spectroscopy appear in the electromagnetic spectrum? You all would have seen electromagnetic spectrum starting from X-ray or gamma ray up to radio frequency region. In different region of the electromagnetic spectrum, you see different types of spectroscopy, molecular spectroscopy can be studied. Now, the question is, where does NMR come in the electromagnetic spectrum? We can find out. Now, in the resonating condition I have put, let us take the magnetic field as 2.35 Tesla and substitute in this equation. I know 2 and I know pi, I know gamma for proton, whose value is given here. It is 26.753 into 10 to the power 7 radians per Tesla per second, and substitute this value. We do simple, take your calculator and calculate, it turns out to be 100 megahertz. New resonating frequency of protons at 2.35 Tesla is around 100 megahertz. Now, what happens if I increase the magnetic field? I changed it from 2.35 to 14 Tesla. Then again put these values, everything remains same, only magnetic field is different, gamma 2 pi is same. You substitute this value, it turns out to be 600.36 megahertz. So, that means you change the magnetic field by 6 times, from 100 megahertz it became 600 megahertz. So, like that, it is linearly varying, that is the matter. Now, what will happen to the different nuclei like carbon? This is as far as the proton is concerned, because I substituted for the gamma of protons. Now, where does carbon come? In the same magnetic field. For gamma value of carbon is 4 times less than that of the proton. Remember, it is 6.72, unless in the case of proton it was 25 point something I wrote earlier. So, gamma is 4 times less. That means nu is also 4 times smaller. That means in the proton it was 100 megahertz, now it is 25 megahertz, 4 times smaller. Same thing, for example, for 14.1 Tesla, you substitute, it turns out to be 150 megahertz. There it was 600 megahertz for proton, carbon is 150 megahertz. So, gamma is the one which is dictating for the resonating frequency. What is the resonating frequency for different nuclei? You can find out by different gammas. Okay. So, that means you can calculate in a reverse way also. Let us say I have protons and I do not know the spectrometer frequency. I record the NMR spectrum. I know it resonates at 300 megahertz. Then if you ask me what is the magnetic field? What was the magnetic field at which we got the resonance of 300 megahertz? Do the reverse calculation. Nu is equal to gamma b naught over 2 pi. So, then b naught becomes 2 pi nu over gamma. Substitute the value of 2 pi and then frequency of 300 megahertz, and then gamma is 26.753 into 10 to the power 7 radians per Tesla per second, and you calculate magnetic field is 7.04 Tesla. So, all the time we are dealing with the magnetic field in Tesla. For different magnetic fields starting from 2.35 Tesla, I showed you we keep on increasing the magnetic field, and resonating frequencies are always coming in megahertz region. Okay. This is where the question comes. Radio frequency ranges always go between 20 kilohertz to several gigahertz. What is the frequency we calculated for different nuclei now? For protons, it was 100, 600 megahertz, carbon 25, 150 megahertz. That is within this range. That means the resonating frequency or the NMR always comes in the radio frequency region, because the radio frequency ranges between 20 kilohertz to several gigahertz, and we calculated the resonating frequencies. We saw, for example, 20 kilohertz to several gigahertz, if you consider, NMR is detected in the radio frequency region. So, that is why all NMR spectrometers operate at megahertz frequency, which is in the radio frequency region. If you go to NMR spectrometers, any spectrometer laboratory where you have NMR spectrometers, you will see that you will see a big a sort of cylindrical objects like that. They are called strong magnets. You can see it is 300 megahertz here, and you can see here, for example, 500, 400, 900 megahertz. All these numbers are written here. What are these numbers? They are the resonating frequency of protons in a corresponding magnetic field given there. For example, if I say 900 megahertz, in this magnetic field the protons resonate at 900 megahertz. In this magnetic field, protons resonate at 400 megahertz. So, all spectrometers are referred to the proton frequency in a given magnetic field. So, that is what you please remember, they all come in the radio frequency region. So, resonance frequencies of different nuclei in a different magnetic field, let us see. We can see proton, nitrogen, carbon, fluorine, varieties of nuclei you can see. Let us see, I have a 4.68 Tesla magnetic field. Proton comes at 200 megahertz, fluorine comes at 188.2 megahertz, similarly carbon 50 and nitrogen is 20.35 megahertz, all in megahertz range. Why? Because the gammas are different. So, you know that I told you gamma of carbon is 4 times smaller. So, at 200 megahertz gamma is 4.68 Tesla, proton has a resonating frequency of 200 megahertz, carbon is 4 times smaller, 50 megahertz. Nitrogen is 20, that is 10 times smaller. So, that means gamma of nitrogen 15 is 10 times smaller than that of proton. So, at 4.68 Tesla, these are the resonating frequency of different nuclei. Now, what happens if I change the magnetic field? You see, from 4.68 I change to 9.39, proton becomes 400, and then similarly carbon 13 doubled and this doubled, everything get doubled because I change the magnetic field into double. Of course, it should be exactly double. 68 if you multiply by 2, there is some multiplication mistake, do not worry, it should be 9.36. Okay. So, similarly at 11.74 Tesla you can see different resonating frequencies are different. So, different magnetic field, different nuclei, we have different resonating frequency, all can be individually studied. Now, let me give you some classical analogy. Classical analogy is like this. Of course, this normally nobody uses, but I am just telling for the sake of making you people understand. Let us take spins, an ensemble of spins, put it in a given magnetic field. I will consider case of spin half nuclei. In the magnetic field, if it is 0, look at it, all the spins are randomly oriented. There is no preferred alignment of the spins. Every possible orientations you can think of. On the other hand, you put them in a magnetic field. This here random orientation is there. As soon as you put it in a magnetic field, it is non-zero, very strong homogeneous magnetic field, that is very important. Then you see spins are aligned here, some in the direction of the field, some in the direction opposite to the direction of the magnetic field. This is called the removal of degeneracy, some spins up, some spin down. Okay. So, this is the classical analogy what we discussed in the quantum mechanical concept, separation of the energy level. The same thing in the classical analogy, we can say the spins which have different types of orientations in the magnetic field in the absence of the magnetic field. So, and another important concept we should know here is more spins are aligned in the direction of the magnetic field than opposing it. It is something strange, right? It is true. It is because of the Boltzmann population distribution. You will understand when you go to the Boltzmann population ratio, we can calculate and see. There are more spins are always aligned in the direction of the magnetic field than opposing it, and this is the lowest energy option. Remember, this is the lowest energy option is more spins should be in the direction of the magnetic field. They are opposing it. And once you put the sample in the magnetic field, we also have what is called a classical phenomena which we understand. There are two forces acting on the spins in the magnetic field. One, the large static external magnetic field ensures that the spins are oriented in the direction of it, aligned with it, here or opposite to it, direction of it. But the spin angular moment wants to keep it spinning at a restricted orientation. Quantum mechanically, we calculated the magnitude and also theta, cos theta I told you calculated, and it turns out to be 54.7 for MA equal to plus half. We found out it wants to be in a particular restricted orientation. And what will happen? Because of this, there exists a sort of a torque. It's a tug of war goes between the spins. Then what happens? The spins will start undergoing precession. It's called precession, circular motion around the magnetic field direction. This is the magnetic field. It starts going in the direction of the magnetic field, undergoing precession like this. This is called Larmor precession. Okay. So this is how it happens. The spins which are oriented in the direction of the magnetic field, spins which are oriented in the direction opposite to the direction of the magnetic field, like a cone, these millions and millions of tiny magnets which are present in the sample start undergoing precession simultaneously. Okay. And alpha and beta components form two different types of cones like this. And this type of precession is, as I said, is called the Larmor precession. Okay. Then you may ask me a question. They are undergoing rotation, that is called precession. What do you mean? What is the frequency of this precession? How fast they are rotating? That depends upon the strength of the magnetic field. Larger the magnetic field, you have the rotation of the field, the precession frequency becomes larger and larger. Higher the magnetic field, higher the precessional frequency. If I increase the magnetic field, they rotate very, very fast. Okay? This precessional frequency is called Larmor frequency. Remember, we also had calculated resonance frequency nu equal to gamma into B naught over 2 pi. I said it is a resonance condition. That frequency is called resonance frequency, which is nothing but Larmor frequency. The frequency at which the nuclear spins are undergoing rotation or precession in a given magnetic field along the direction of the magnetic field. This is called Larmor precession. Okay. Now the question is, you ask me, what is the energy involved? See, in the varieties of molecular spectroscopy techniques, in this table you can see starting from cosmic rays, gamma rays, etc. You can see wavelength, frequency and energy in the last column. Radio frequency comes in the last row at the bottom of the table. That means look at the energy. Some of the energy is very positive. For example, gamma ray 1.10 to the power of 6 into it goes up to 10 to the power of 8. Such a large interaction energy. Whereas the radio frequency last one you see 10 power of minus 7 to 10 power of minus 3. Very, very weak interaction. Energy of interaction is very weak in NMR. The beauty is this weak interaction is the strength of NMR. Because of this, you can understand, you can study the minute perturbation of the electronic charge distribution at the site of the nucleus can be very easily studied by using NMR. So the weak interaction energy is actually the strength of NMR. Okay. So now with this I will introduce what is called sign of gyromagnetic ratio. I said mu is the magnetic moment, P is the angular momentum. If both of them have the same sign, they can have a difference in positive or negative. If both of them have the same sign, then gamma is positive. If both of them are opposite sign, gamma is negative. So how does it matter? See, if the magnetic moment and spin both have the same sign, orient in the same direction, gamma is positive. In other direction, other one gamma is negative. Some nuclei, for example, nitrogen 15, silicon, tin 119, they all have negative gamma. You may ask me, so what? Positive or negative is a simple number. How does it matter if it is positive or negative? It has an importance as far as the precision is concerned. For example, the sense of precision changes with the sign of gamma. For example, for gamma greater than 0, it is rotating clockwise like this. For example, proton. You put the protons in the magnetic field, they start rotating like this in the clockwise direction. Similarly, carbon, all nuclei with gamma greater than 0, which are positive, rotates like this. Now what about other nuclei with gamma less than 0? See, now they are rotating in the opposite direction. Like nitrogen 15 and silicon, the sense of precision for the sign of gamma is different, the sense of precisions will be different. One goes in the clockwise precision, otherwise anti-clockwise precision. They are very important in NMR when you want to understand lots of things. Okay. Now I will introduce a term called population difference here. What is the population difference? The distribution of spin populations between alpha and beta spin states in NMR is given like this. I told you there is energy separation in the magnetic field for minus half and plus half spin states, and we also calculate the difference in the energy delta E. But what happens is there is a distribution law called Boltzmann distribution law, according to which the more spins are aligned in the direction of the magnetic field than opposing it. This is a very important condition called Boltzmann distribution condition. NMR signal, what you are going to detect here is the difference in the spin population. If both of them are equal, what will happen? Population difference is 0. That means you do not see signal. There must be difference in population, only then you can see the signal. So NMR signal is the difference in the spin population between two energy states. Okay. So distribution of spin population in different energy state is governed by what is called a Boltzmann equation, which is given like this: n beta over n alpha, beta and alpha are the spin states, and n beta and n alpha are the spin populations in the alpha and beta spin states, and this is given by an exponential law E equal to minus E alpha E beta minus E beta over kT. So if you know the difference in the energy between alpha and beta spin states, you know what is T temperature, K is a Boltzmann constant, you can find out what is the population difference. Very easy, you can do that. E alpha E beta I know what is delta E, I know what is the Boltzmann constant, its value, I know what is temperature T, which is in Kelvin, I can calculate everything. So with this, now let us see what will happen to NMR sensitivity. Can I calculate that? There are factors that govern the NMR population difference. One is the magnetic field, other is the temperature. For example, for detection of NMR signal, there must be spin population difference, I told you. Now when there is no population difference, I also said there is no signal. How magnetic field and temperature govern this population difference? Let us see that. And this is the population difference delta E, which I showed in the 2 slides before. I know what is gamma, I know what is Boltzmann constant, I know what is energy, and I know magnetic field. Simply substitute all these parameters in this equation. Calculate. Delta E turns out to be 3.9 into 10 to the power minus 25 joules. I know Boltzmann constant. I know the temperature, ambient temperature 298 K, and in a given magnetic field should be always in Tesla, it is 14 Tesla. If you do that, what are you going to see? Calculate this, substituting this value, and population difference, if you calculate delta value substituting this, now n beta by n alpha turns out to be 0.999904. What do you understand by this ratio? It is close to 1, 0.999904. That means n beta over n alpha is almost equal to 1, which tells you the population difference between beta states and alpha states are almost identical, with a negligibly small difference in populations. And you can calculate this at room temperature. If I consider 2 million proton spins and take a magnetic field of some, let us say 14 Tesla, I calculated by putting it myself, by putting into that equation, and I calculate the population ratio, and it turns out to be 0.99904. Then I calculated how many spins are there in the alpha state, how many spins are there in the beta state, and I found out the difference is 96. My God, look at it. There are 2 million nuclear spins I took as an example, and at the room temperature in a given magnetic field of 14 Tesla, I found out the population difference is only 96, and that is what we have to detect, difference in spin populations. Okay. The small population difference which we have to detect, what does it tell you? NMR is highly insensitive technique, very, very insensitive technique. And there is something which I want to tell you about sensitivity and the magnetic field. Now, let us see what happens if I change the magnetic field. When I change the magnetic field, I told you Zeeman interaction of the nuclear magnetic moment with the magnetic field is larger. Larger the interaction, larger the population difference. That means energy separation becomes larger and larger if you increase the magnetic field. Smaller the separation magnetic field, smaller the energy separation. So, larger the population difference means larger energy separation, smaller population difference means smaller energy separation. So, that means the magnetic field has a direct relevance as far as the Zeeman interaction and the population difference is concerned. It clearly tells me higher the magnetic field, higher sensitivity. Okay? Population difference at different magnetic fields I have calculated. You can see that I started with 2 million spins. In the absence of the magnetic field, B naught equal to 0, states are degenerate. There is no separation of energy levels. All spins are in the same energy level, randomly distributed. Now, at 2.35 Tesla, there is a separation of the energy levels and the population excess is very small, only 16. Here 64. When I change the magnetic field, 4 times larger here. See here 32 and 32. Whereas I again increase further, it becomes 96. That is what we calculate for 14 Tesla. Now, even increase further also, it became 130. What does it mean? You increase the magnetic field enormously up to 18.8 Tesla. Remember, such a large magnetic field, to get homogeneous magnetic field is not an easy job. It is very, very challenging. It is not easy. Nevertheless, if you get it, what gain we got? From 0, we could get only difference of spin population of only 130. Is it worth the exercise? Yes, even though it appears like this, but in turn you will see there is a big gain in the sensitivity by going to higher magnetic field. So, higher the magnetic field, you will see the sensitivity goes to the power of B naught to the power of 3 by 2. B naught is the magnetic field, static magnetic field, and to the power of 3 by 2 you will see that. You can see as I keep on increasing the magnetic field in this direction, the sensitivity keeps going up and up. And it is, remember, the sensitivity with respect to the magnetic field is given by B naught to the power of 3 by 2. So, this is a spectrum which shows you as you keep on increasing the resonating frequency from 400 megahertz, 600 megahertz and 800 megahertz, you see the energy separation you calculate, and the population ratio, if you find out signal to noise ratio here to here. He say here about 600, signal to noise ratio is about 1200, here is about 1700. So, by changing the magnetic field, you are increasing the sensitivity. So, higher the magnetic field, higher the sensitivity. So, this is another important factor, magnetic field, which governs the sensitivity of the detected NMR signal. So, now the time is up. I am going to stop here, but let us summarize what we discussed today. We started discussing about the interaction of the magnetic moments with the magnetic field. We calculated the energy for different energy states and equated that to find out the resonating condition. Nu is equal to gamma into B naught over 2 pi also we worked out. And then we also gave the classical analogy. We calculated what is the Larmor precision frequency, and we found out for a given magnetic field what is the resonating frequency of a proton, what is the resonating frequency for the carbon at different magnetic fields, and we found out they are all in megahertz range. And what is megahertz range? Radio frequency we know it ranges from kilohertz to gigahertz range. So, we understood NMR spectroscopy appears in the radio frequency region. And if I know the radio frequency, resonating frequency of protons in a given magnetic field, if I do not know the magnetic field, once I know the resonating frequency, because I know gamma, I can even calculate what is the strength of the magnetic field. And we knew by calculating the population difference, the sensitivity of NMR is very, very low. And we saw by increasing the magnetic field, the population difference can be enhanced, not enormously, but still it is sufficient enough to get the good signal to noise ratio. So, sensitivity also depends upon the magnetic field, which in turn depends upon the energy separation it increases energy separation, and we understood Boltzmann population ratio is the one which governs the population difference between two energy states. So we understood NMR is insensitive technique, magnetic field, by increasing we can get the sensitivity. That is what we understood today. We will stop here and continue from this in the next class. Thank you.